you very much. Thanks very much to Christina and the organizers for inviting me to this very nice place, this very nice workshop. So yes, I want to tell you a bit about magnetic imaging on the nanometer scale, a bit from an experimentalist perspective of a little bit of why we want to image nanoscale magnets, how we do it in particular, and I'm going to show you a few examples at the end on two-dimensional magnets that we've imaged using some techniques that we've developed. Because I know there's also a few of you interested in skyrmions, we've measured also at the surfaces of bulk chiral magnets, and if I have time, I'll show that, or you can ask me about that later. Before I start, let me just thank the people in the group who actually do the work that I'll show you. So this is my group in Basel, full of postdocs and PhD students. Actually, Paritosh, who is a research scientist in my group, is here and has a poster about one of the things I'll talk about. So yeah, you can talk to him about more experimental details. The group actually works on quite a lot of different things, spanning superconducting thin films, 2D magnets, chiral magnets, also a little bit of mechanics and optomechanics. What I'll talk about mostly here has to do with two-dimensional magnets and scanning probe sensors that we use to image these kinds of very weakly magnetic systems. So just a quick outline of the talk. I'll just start with an introduction. I'm going to tell you a little bit about how one images magnetism via essentially by measuring the stray field that a magnet produces. I'll talk about two specific types of techniques that are used in our lab mostly and that we've developed to become very sensitive, so magnetic force microscopy and scanning split microscopy, and to try to motivate them, I'll give you examples of experiments we've done in different 2D magnetic systems. Some of these experiments, especially the last ones, are very new and still, well, we still have some things to understand that are not yet, let's say, fully finished projects, and then I'll have some time to conclude. So I usually like to start talks by showing this image, which is something that maybe you've seen from your early bachelor's in physics 2 or something like this. This is an image made in the 1800s using some iron filings of the magnetic field, the stray magnetic field from some ferromagnets. And I just show it first of all because it shows the beauty of magnetic imaging, but also the idea here is that this contains a lot of information. Right? There's a lot of information about the dipolar interaction between these magnetic fields, of course, about Maxwell's equations, and in fact, it's not an accident that this happened around the 1830s before the development of all the equations behind electromagnetism. So magnetic imaging research is important also from a research point of view in order to reveal what's going on, let's say, locally in a system, what's going on in terms of defects, what's going on in terms of length scales, and I think that continues to be true today. So this is, a more modern version of that image taken in our lab. Actually, it's a series of images taken at the surface of a chiral magnet, the copper oxoselenide, which is a skyrmion host, by one of my former postdocs. And what you can see here as you go from very high out-of-plane applied field to reverse field is that the system at the surface presents very complex nanometer scale phases. So it goes through a number of different phase transitions and shows different nanometer scale magnetization patterns. So you go from like trivial polarized state through some kind of conical state with a helical period on the order of 60 nanometers, and then you go to some kind of surface state, and ultimately you even get to see some kind of disordered skyrmions trapped at the surface. So I'm not actually going to talk about the details of this, but if you're interested, we can discuss this later. But this is just to show you that there's a lot of information in here. There's a lot of things that you can get from this image that you can't get from, let's say, a bulk neutron scattering image that essentially averages over the entire bulk of the sample. And here, for instance, in this kind of transition between phases, we actually see coexisting spin polarized phase, conical phase, and skyrmion phase all together. And there's some quite complicated domain structures here that we still have to understand. That, let's say, in a common bulk measurement would just would be averaged over. This is at low temperature. This is a low temperature skyrmion phase, so it's not the typical pocket around 50 Kelvin. This is the low temperature skyrmion phase, so at 4 Kelvin. Okay, but actually, so that's an example, let's say, of imaging what you might call quantum magnetism. But the kind of quantum magnetism that I want to talk about today, or another type of interesting quantum magnetism that you might want to image, is the magnetism that comes out of 2D materials. So I'm sure many of you are aware of, in the last 15 to 20 years, the revolution, let's say, in the engineering of 2D materials. So we have van der Waals structures like graphene, but also all kinds of other structures that we can essentially exfoliate and stack on top of each other, even when they're not lattice matched. We can twist them. We can put different types of materials on top of each other. And this has opened up a whole zoo of possibilities in terms of what kind of materials you can engineer. So you can engineer metals, semiconductors, insulators. You can engineer the band structure. And you can also, in principle, engineer magnets, starting from essentially two-dimensional versions of magnet, or even starting from materials that are not magnetic. So this is also a very interesting, and we heard it, I think, in the morning, the talk about twisting magnetic materials, that you can really study, in theory, interesting systems and hopefully experimentally also realize them. Of course, with all of this control comes also a lot of disorder. So these kinds of systems are very sensitive to strain, to all kinds of external degrees of freedom, because essentially they're all surface area. And so understanding things at short length scales becomes very important. So making images to understand how long the coherence length in these systems is very important. And often if you do a bulk measurement in such system, you're averaging over a lot of details on the microscopic scale that you should be able to see via imaging techniques. So that's one of the reasons that we're very interested in measuring two-dimensional magnetic systems. Probably many of you have heard about lots of the nice things that you can engineer in 2D systems. Of course, the canonical example is the magic angle twisted bilayer graphene, in which you could engineer superconducting state, among other states. There are also two-dimensional magnetic systems, like this antiferromagnetic layered system, chromium triiodide, and there are many, many others. Okay, if we focus just on the magnetic 2D systems of interest, you can imagine, I think, as many of you as theorists, what kind of interesting things you could, let's say, engineer. So you can engineer systems that are essentially two-dimensional Ising models, or XY models, or Heisenberg models, and then investigate the stability of these against various external parameters. See, for instance, whether these things have long-range order or not, depending on different things that you can change. 2D is an especially interesting, let's say, area to work in, because if you plot, so this is stolen from a nice review paper from 2020, if you plot essentially spatial dimension and you look at 2 dimensions as a function of the spin dimensionality, in 2D you really have quite a lot of different behaviors. So you go from systems that can demonstrate long-range order to no long-range order to things, to very interesting regimes in between. So, of course, other dimensionalities are also interesting, but this is a very rich region, let's say, of the phase diagram. And of course, this has been recognized for many, many years. So people have not been studying 2D magnetism just since we started exfoliating magnetic materials, but this has been going on for decades in the form of thin ferromagnetic films, also in bulk systems which are layered, where the layers don't talk to each other very well magnetically. But what has changed in recent years is exactly the fact that you can start using van der Waals materials, so materials that are easily exfoliatable on an atomic scale, stacking them together and then looking at their magnetism. And that started more or less in 2017 and is a growing, let's say, field of material science and also physics investigation. And so this is what I want to talk about now. I want to talk about how we can actually study these systems experimentally, and specifically how we can study them, let's say, how we can make images, how we can study them on a local scale, keeping in mind that disorder is still a very important problem in these systems. So the question that I want to ask is, so how should we measure these 2D magnets? Now, many of you know many different experimental techniques for measuring magnetism, so neutron scattering, muon, spin rotation, NMR, ESR, all kinds of X-ray techniques that I think we'll hear about in the next talk. We can measure magnetization, susceptibility. Most of these are, except let's say some forms of X-ray and STM, these are bulk measurements. essentially require large samples and average over large length scales. STM, of course, is a very local probe, but requires very specific samples. It requires tunneling, so you need a conducting sample with a very, very clean surface. X-ray is actually a very interesting technique that I guess we'll hear about before. I won't talk about it because I'm not an expert, but it's a very interesting technique also for measuring 2D magnets. But the kinds of techniques you need to be very sensitive, because 2D magnets the volume is very thin, so it's atomically thin. They contain few moments, so you have to be sensitive to very, very subtly magnetic systems. Correlation lengths are short, so you need a technique that has a high spatial resolution. So this is, let's say, our requirement. And if you start thinking about this a little bit, some of the best techniques for doing this are essentially scanning probe techniques, so very sensitive techniques where you measure something at different positions in space and you move your probe as you measure it. And you can look at this, actually this nice review from Review of Modern Physics, where they treated a question in, well, they discussed many different types of magnetic measuring techniques, and if you think about something that has high sensitivity and high spatial resolution, you essentially want to be in this corner of this graph. So this graph shows equivalent magnetic noise, so this is something proportional to the sensitivity. So the lower down on this axis you are, the more sensitive you are to small magnetic fields. And here, this is effective linear dimension, so the lower down you are on this probe, the higher spatial resolution you have. And if you kind of go up to this corner and look what kind of techniques do we have, the techniques that are here are magnetic force microscopy, scanning nitrogen vacancy center microscopy, and scanning squid microscopy. So these are techniques which essentially map weak magnetic fields produced by magnetic moments and allow you to image them. So I'm going to talk a little bit about MFM, and I'm going to talk about squid. I'm not an expert in NV microscopy, so I'm not going to talk about that, but that's also a different type of, let's say, very relevant technique. So the idea here is we use a technique, that scanning probe, that measures stray field, and then from this measurement of stray field in space, we can reconstruct what's happening in the sample underneath us in terms of of the magnetization configuration. Okay, and if you just think about that from a very basic point of view, what does that mean? Let's say I have a 2D plane of uniformly magnetized material, right? What kind of stray field will I measure from that? And if my 2D plane is infinite, as I guess many of you theorists would like to have a nice uniform infinite plane, the stray field from that above it will be exactly zero. Okay, so you will measure nothing. Why? Because each magnetic moment can just be modeled as a bound current, and then you add them all up and you'll get a big bound current at the edge, and so you send the edge to infinity, you have no magnetic field. So in fact, in order to image these things, you also have to keep into account that you need edges. Right? So this is just a very simple model of say 1 by 1 micron magnet, 2D magnet, with some uniform out-of-plane magnetization, and you can see that the signal essentially here is due to bound currents at the edges, and the bigger you make this, the smaller the field will be here in the middle. Okay, so the other problem with measuring the stray field is, of course, if you measure the stray field, but what you're actually interested in is the magnetization underneath, you essentially have to invert the Biot-Savart law. Okay, and under certain boundary conditions, inverting the Biot-Savart law is okay. It's a well-posed problem, but in general, it's not. So if I have a three-dimensional magnet and I measure just the stray field around it, there is no unique magnetization configuration of that 3D magnet that makes that stray field. So I cannot invert that problem in general, so I need some boundary conditions. Fortunately for the 2D system, if your magnetization is confined to 2 dimensions, and let's say pointing along the z direction, that's an invertible problem. But as soon as I let the magnetization point in any direction, that's no longer invertible, and I can't in general come up with the magnetization. We can still learn things from the stray field about the configurations, especially if we compare to simulations, but we can't always determine them exactly. Okay, if you're actually interested in some of these things, I would point you to this review that we wrote together with Christian Dagan, who works on NV microscopy and similar problems. And we really try to address what are the best techniques for measuring 2D materials, both 2D magnetic materials and also 2D materials where we're interested in measuring current densities and mapping where currents flow. Okay, so let me now switch gears a little bit and just talk about one specific technique that we use, and then an example of how we use it to learn something in a two-dimensional magnet. So the technique I want to start with is magnetic force microscopy. I guess many of you are familiar with this. This is a very old technique that was born in the 80s after the kind of all the revolution in scanning probe microscopy started, after they invented STM and atomic force microscopy. And the idea is just that you take a mechanical cantilever, so some kind of compliant object, and you coat it with some magnetic material such that the tip is magnetic, and you scan it above some magnetic material, and there will be a force on that tip that depends essentially on the stray fields produced by the sample underneath. Okay, and in fact, if you go a little bit more into the details, the frequency shifts or the contrast that you typically measure here are proportional to different types of magnetic field gradients along different directions. And this is a very nice technique because you can get very high resolution, in the best cases down to something like 10 nanometers, but in general more on the order of 100 nanometers. Now the big problem with this is these cantilevers are typically very stiff. So these are pieces of silicon, kind of microns thick and maybe hundreds of microns long, and they have large spring constants on the order of 10 or 100 newtons per meter. And that means that if you're trying to measure the magnetism of a single atomic layer, like you have in a 2D magnet, you won't get very far with such a probe. It just will not deflect very much. So in our own group, we asked ourselves, how do we make a magnetization or an MFM which is sensitive enough to measure such small signals? And of course, the easiest way to do this is to just reduce the size of the mechanical transducers, of the mechanical sensor. So you go from something which is like a large silicon object like this, and by large I mean something that's maybe the diameter of a hair long, so it's still not very large, to something much smaller. Ideally you would go to something maybe on the atomic scale, like this carbon nanotube here. Of course the carbon nanotube is not so nice because it's so thin that it very quickly becomes a nonlinear mechanical object, and that becomes very difficult to control. So we make some kind of compromise, and we try to use essentially a nanowire as our mechanical transducer. Now, of course, if you want to use a nanowire as an MFM, you need to make it sensitive to a magnetic contrast, and so you need to functionalize it with some kind of a magnetic tip, or you have to make the nanowire itself magnetic. This is a very early version that actually a PhD student of mine, Nicola Rossi, did with some collaborators in Regensburg. So they got a nanowire grown out of gallium arsenide with a manganese arsenide ball at the end, which served as a magnet, and tried to use this as an MFM. And in fact, you can see it's in this funny geometry where the nanowire is hanging in the pendulum geometry above the sample, and then there are some interaction forces between this little magnetic tip and the surface. And the reason we do it like this is because this object is extremely soft, and if we were to hang it over the sample like this, it would immediately snap. So you essentially exploit the fact that this is soft in flexural motion this way and very hard in the axial motion this way. This was an early version of what we now use. In fact, now in order to optimize this, what we do is take silicon nanowires that growers in Waterloo in Canada grow for us that are about 20 microns long and maybe 100 nanometers thick. And then what we do is we deposit, using a focused electron beam technique, a little tip made out of cobalt here. Okay, so then we have a very nice mechanically thin and compliant nanowire with a very, very tiny, highly magnetic tip on the end. And in this way, we should be sensitive enough to measure things like two-dimensional magnets. Of course, I'm not going to get into the details here, but you have to build a special microscope in order to measure the motion of this and in order to scan it over your sample. But suppose that you can do that, then you can just imagine scanning this over the sample and measuring essentially the mechanical response of this nanowire to the magnetic stray fields of your sample underneath. So I want to tell you about how it's an optical detection, so we use a laser here. It's not very realistically drawn, but essentially we send a laser beam, it scatters off the nanowire, it reflects back, and there's a small interferometric signal, and so we can measure the motion of the Okay, so we use this to measure a two-dimensional sample from collaborators. It's 2 layers of europium germanium that were grown by MPE. This is an interesting magnet because it's in the monolayer, it's a ferromagnet with an easy axis in the plane, and in the bulk, it's a stacked antiferromagnetic, right? So it's an in-plane, easy axis ferromagnet, and then antiferromagnetic interlayer. And what happens is that there's a kind of layer-dependent transition from the antiferromagnetic state to the ferromagnetic state that doesn't just happen suddenly as you go from the bilayer to the monolayer, but it seems from bulk measurements that this kind of slowly happens as you reduce the layer number. And there are some indications in bulk measurements done before we studied this that essentially that there is some region of thickness where there's a mixed phase. Okay, so there are some regions, let's say call them domains that are antiferromagnetic and some that are ferromagnetic. So we were interested in mapping this. Could we see this, let's say this mixed phase? Right. So in order to do this, of course, we need a sample. So we got this sample from our collaborators, and they patterned them into these shapes because, of course, we need edges so that we can detect the magnetism with our scanning probe technique. So we don't want, let's say, an infinite plane of this bilayer, but we would like little bar shapes or oval shapes or things like this so that we can make an image of them above. So we're going to concentrate on this little bar shape over here, and then we're going to image it with this nanowire, which had this cobalt tip here, which is colored in blue so you can see it. It's not particularly sharp, so we had some problems here in the growth process, but it was good enough for the experiments here. And what we first did is make a measurement of the magnetism of the system just to make sure that our sensor is sensitive enough to just measure the magnetism of these two layers of two atomic layers. So what you see here are images of the frequency shift, so the standard, let's say, MFM signal that you would measure above this the piece of this rectangle at different applied fields out of the plane. Okay, and so what you would expect is that as I raise the applied field out of the plane, you slowly cant all the spins, and you should uniformly magnetize this thing. And because we measure essentially signal around the edges, what you expect is that the edges of your MFM image light up more and more, and that's exactly what you can see here. And you can see that maybe a little bit more quantitatively if you take a line cut across here and plot that, and you see that the signal gets bigger and bigger as you go to higher and higher field. And in fact, if you plot the amplitude, you can kind of make a magnetization curve, something equivalent to a magnetization curve, where you see that it starts to saturate around 4 Tesla, which is also what you observe in bulk measurements. So it seems that it works. We're sensitive enough to measure this very, very small magnetic signal. So the second experiment was more interesting. So what we do in the second experiment is we essentially go into remanence, we go into zero field, we go above the magnetic phase transition, which is around 10 Kelvin, and then we cool through the magnetic phase transition, and we image the sample as we cool. Now what I'm showing you here are two signals. The first one is the same as before, so frequency shift, and the second one here is dissipation. So we're measuring this mechanical object. You can imagine it's shaking over the sample like this, and you can measure, of course, the resonant frequency of that, so it's proportional, as I said, something like the gradient, and you can also measure the energy loss of the system. So the tip and the sample are interacting, and there can be, let's say, loss mechanisms that increase the mechanical dissipation of the cathode. And that's exactly what you see here. And if you look carefully, what you can see is that as you go through the phase transition, and these signals here are basically integrals of what you see over the magnet, they get peaked, both the dissipation and the frequency shift right around the magnetic phase transition. And this was very puzzling to us in the beginning because in principle you would expect that as you cool the system through the phase transition, so in a zero field cooling, there's no preferred direction, and in fact all the frequency shifts, although you might have some, they should in general add up to zero. But you can see that they always came out, they're always positive, they always have some specific direction. And it turns out what's happening here is actually we're making measurements not of the stray field, but actually of the local magnetic susceptibility. So you can imagine that this magnetic tip, it's actually producing a relatively large stray magnetic field on the order of 10 millitesla or so, and as it's oscillating above the sample, it's changing the local field at the sample underneath. And the magnetization of the sample is responding in some way, in some parts in phase, in some parts out of phase, and this then acts back on the cantilever. So it turns out that this signal here in the frequency shift is proportional to something like chi prime, so the in-phase susceptibility, and and this one is like chi double prime, the out of phase susceptibility. And then, of course, it makes a lot of sense that these signals are peaked at near the magnetic phase transition. What you can also see from these images is very fine structures here on the order of 100 nanometers or so, and we think that this has to do with this phase separation, so that this indicates domains of ferromagnetic and antiferromagnetic phase, because they should have different response in the susceptibility. Fortunately, this is just some evidence. We would need to do quite a bit more experiments to put this on solid ground, but very unfortunately, these samples came from Russian collaborators, and unfortunately, we couldn't continue this collaboration anymore for reasons beyond our control. Okay, so let me go on then with another type of sensing technique and another experiment that we've done. So now I want to tell you a little bit about superconducting quantum interference devices and how we can use this as a scanning probe. So probably most of you are familiar with squids. So squids are essentially loops of superconductor with two Josephson junctions. Yeah. Yeah, so it's fixed at the cantilever frequency, and so this is at something like 300 kilohertz. So they should be slightly different temperatures, I think, also from the bulk measurements, but they are anomalously different here. You can see one is really right a little bit above 10, and the other one is around 6, and I don't have a good answer for that. Okay, yes. If I'm going too fast, please stop me. Ask me more questions. Right, so I was talking about superconducting quantum interference devices. So they're excellent magnetic field sensors. They can also be excellent scanning probes, and this is not something new. This has been used for many, many years. And the basic idea is you make a squid, and you essentially make a measurement, and you move it to the next place, and you make another measurement, and so on. And so you, by the fact that you're making measurements of magnetic flux, with a device of fixed area, you can then extract the magnetic field profile in so doing. In the past, this has been difficult. Let's say it's been difficult to study nanomagnetism with such things because the squid loops were just in practice very difficult to make small. So most squid loops were in the micron scale or much, much bigger. And also, the Josephson junctions that were used, so superconducting Josephson junctions, typically had upper critical fields below 10 millitesla, meaning that essentially you couldn't measure anything in a significant magnetic field. And so for many, many years, these were essentially just used to measure superconductors, superconducting vortices, and so on. What's changed is that in the past few years, new types of squids have been developed, in particular by the Zeldov group and Weizmann, which are extremely small, so have diameters on the order of 50 nanometers or less, and can go up to fields up to 3 or 4 Tesla. So this now makes them really very interesting probes for magnetic systems. So I want to tell you a little bit about what we've done in terms of developing these, trying to make them easier to use, and how we apply them. If you're curious about that, there's a good chapter in this roadmap article about this. Not finding. So this is, let's say, what happened 15 years ago, that the Zeldov group invented this scheme called the squid on tip, where they essentially take a glass capillary, they shoot it with a laser, melt it, and pull it so that it's very, very, very narrow, and makes a tube with a little hole that has a diameter down to 40 or 50 nanometers, as I was saying. And then they use a directional evaporation technique to evaporate superconductor on one side and the other, and then on the bottom, and it forms these two superconducting leads and a loop with two die-in bridge constriction Josephson junctions. And by the miracle of experimental physics, this somehow works very well, and you can use this as a very nice probe. So yes. It's larger, yeah. So you have to play with, this is actually all the material science that goes into this. You have to get the material, and you have to get all these things to work. Otherwise, the sensor doesn't work. It's a usual squid. So this is done with several materials. I guess the best one from the point of view of noise is lead, which is unfortunate because lead is an awful material. But we also learned how to use this, how to make these. It took us several years, and we can now also make these in our own lab. And you can do really beautiful things. You can use these as very sensitive field sensors, temperature sensors. You can make very nice images. But it's really terrible on the graduate students because these things are difficult to make and they don't survive very long, and they're very, very fragile. So you can imagine, I try to hit it home by this picture that you see here. This is basically just a glass needle with a 50 nanometer tip that you have to bring 50 nanometers close to a sample and scan it around for multiple days, right, without touching. And that's a big problem. So the usual way that people doing scanning probes solve this is they couple these fragile probes to some kind of mechanical oscillator, and so then when it comes very close, there are some kind of interactions between the surface and the tip, so electrostatic or van der Waals, and these forces essentially slightly change the mechanical resonance of this mechanical object, and then you can detect before you make a touch, before you crash. Okay, and the favorite technique to use is to use the so-called tuning fork. This is just like a musical tuning fork, but it's very, very small, and exists in all of your Swatch watches to keep the time. You use these things essentially to stop yourself from crashing. The problem, you can see it here. So these mechanical oscillators are very bulky. Here's another example of one. And these tips are really, really tiny. So what happens when you approach is that you see no frequency shift because this thing is so massive that it doesn't really feel anything. You don't see any frequency shift until you're very, very close. So you can see here the frequency shift that we measure is on the order of tens of millihertz. That's very small. Until you only see it when you're 20 nanometers away. But now you have to imagine your tip is 50 nanometers wide, so 20 nanometers is basically too late. So you've essentially crashed. So some of my students would scold me for showing this because they can sometimes make this work better, but in general, this is the problem. And so this makes the experiments take very long and have a very high failure rate. So in our lab, we spent quite some time trying to improve this, and we developed what's called a squid on cantilever. So the idea was to take an AFM cantilever, which is designed to solve exactly this problem. So it's a compliant mechanical object that when you bring close to a sample, provides a large frequency shift even when you're quite far away. Okay, so you can see here the scale. Now we're talking about a micron, and we're talking about frequency shifts of hundreds of hertz instead of tens of millihertz. Okay, so then the idea is you can just hook this up to your commercial atomic force microscopy setup, and it just controls the distance, and you never have to worry about crashing. Now the challenge is that you have to put the squid here. Okay, so how do we do that? So the way to do that is essentially to take a cantilever. And this was the first thing that we did. We bought a cantilever. We went to what's called a focused ion beam machine, and we cut away part of the cantilever. So the focused ion beam just shoots gallium ions at an object and is able to machine away parts of the sample, so to a nanometer precision. We then spot our superconductor, in this case niobium, which is a very robust superconductor, and then we go back to the focused ion beam and we cut some patterns. And the patterns that we cut form the squid and the Josephson junctions. So this is the actual cantilever. What you can see here are two leads that have been separated by a focused ion beam cut, and then if you focus in on the tip, we have this little structure here which shows a loop and two constrictions which provide the Josephson junction. So now you have an AFM with a Josephson with a squid on the end. Now this is the first iteration of this. It's rather big, and it had a diameter on the order of 300 nanometers. I can show you, we can make them much smaller. But just to show you, then you have these, you can have the same kind of properties of the squid on tip. You can see here the quantum interference pattern as a function of the applied field. So this is periodic in the flux quantum, and it works just like you would expect. It has a very, very nice sensitivity, which is on the order of the squid on tip. So now if you just do a very simple test experiment, so here we have an artificial spin ice array. This is just an array of cobalt nanomagnets on a silicon surface. What you can do is you can take this squid on cantilever and you can make an AFM image of that, so just the topography by measuring the frequency shift. And at the same time, you can also measure the squid current, and you can make an image of the out-of-plane stray magnetic field, which is this. So this is an experimental image, and then you can relate that in principle to what is the magnetization configuration of that spin ice. Okay, so actually these days we can make things much smaller. So after some optimization, we can actually make these squids have diameters, physical diameters on the order of 50 nanometers, which if you then actually check because of flux focusing effects. It's an effective diameter on the order of 150. And then very recently, with collaborators at the University of Tübingen, who have a helium-focused ion beam, which has even higher spatial resolution, we can make holes that are physically 10 nanometers or less, and then we end up with effective squid diameters or spatial resolutions on the order of 50 nanometers. Okay? And this is actually very significant because that's kind of, aside from STM, the highest spatial resolution you can get with a scanning magnetic probe. So also NV centers have sort of similar best spatial resolutions. Yeah. Good question. So in fact, there are two Josephson junctions here and a third one here. And we added a third one because actually then you can add one more lead. So you can see here instead of 2 leads, we have 3 leads. And this provides you the ability actually to smoothly tune this interference pattern. Because if you actually are only sensitive to magnetic field where you have these sharp slopes, and here, places like that, you have no sensitivity, so there are blind spots in the field pattern. And one particularly important blind spot is right at 0 field. And if you have this extra junction, you can essentially shift this and provide sensitivity in principle at all fields. So it's, yeah. So in fact, with this focused ion beam technique, you could make more complex circuits in principle on the cantilever. Okay, and just to show you that you can actually make images that have high resolution, these are some images of the surface of copper oxoselenide, which is of course a helomagnet with a helomagnetic order of 62 nanometers. And I think you can't really see it on this beamer here, but this is the projection of the helomagnetic phase. And you should be able to see here is a sinusoidal oscillation of the field at 60 nanometers that we can see with this probe. So that means that it's sensitive to such small magnetic length scales. And here you can see an image of a cluster of disordered skyrmions. And if you take the line cut through the Gaussian of one of those skyrmions, you'll see that it has a width on the order of 50 or 60 nanometers, which is essentially limited by not the size of the skyrmion itself, but by the size of the probe. It's the point spread function of the probe. This is at 5 Kelvin. Okay, so how much time do I have? 20 minutes. Okay, then I can tell. So let me tell you first about what we did with chromium sulfur bromide, which is a very nice 2D magnet, and then maybe I'll have time for one more 2D magnet. So we were interested in studying chromium sulfur bromide, mostly for practical reasons. It's one of the few two-dimensional magnets that you can exfoliate that is actually stable without having to be encapsulated and so on. So it's experimentally one of the easier ones to deal with, and it's also very, very interesting from a physics point of view because it's an A-type antiferromagnet. So each plane is ferromagnetic, and then in between the atomic layers, it's antiferromagnetically coupled. The Néel temperature is on the order of 132 Kelvin, and it has an anisotropy axis in the plane along the A-axis. And what's very interesting is that, like other 2D magnets, it's very sensitive to external perturbations. In particular, if you strain the system along the A-axis with enough tensile strain, you can reduce the antiferromagnetic interlayer coupling and turn it into a ferromagnetic coupling. Okay? So we were interested in seeing what happens if you have inhomogeneously strained flakes, which you often have, how that affects the magnetic texture, the magnetic state of the system. So we got some very nice samples from collaborators in Colombia. They essentially sent us these strips, which they exfoliate of a few layers of this chromium sulfur bromide. And what they did to these strips is that they pushed them using an atomic force microscope, and they bent them in order to essentially have some strain along this long axis. So with these bent flakes, what you end up having is some tensile strain on one side and compressive strain on the other side. So if this is the flake that we measured most, you can sort of see it here, it's a little bit bent, and by the geometrical bending, you can essentially calculate what is the strain profile across the entire flake. Here you can see we can get up to strain on the order of 0.25, so not quite up to 2%, which is what you need in order to change from antiferro to ferromagnetic coupling, but still interesting. So the first thing we did is we put these things in our cryostat at 4 Kelvin, and we put them down on the surface, and we went with our scanning squid above, and we measured the stray fields above the system. We first do this in magnetic remnants, so with zero applied magnetic field. And what you expect, if you have, let's say, this strip here, and we look at a cartoon of a cross-section of the strip, you expect to have these antiferromagnetically coupled layers in remnants, essentially compensating each other and producing a zero field. So if you have an even number of layers above it, in general, you would expect to see almost no stray field. If you have an odd number of layers, so as you have here, you would see then the signal from one uncompensated layer. And so what we had is this kind of a strip. So if you go over this strip, what you'll find is you have 18 layers, most parts of the strip here, and here where you see a little bit lighter, you have 19 layers, and then here you have 14 layers. And you can see the cross-section of that AFM here. Okay, so what you expect is to have just a little bit of signal from one, this very narrow strip here, equivalent to the magnetization of one layer, okay, in the plane. And if you look at the image of the magnetic field out of the plane, that's exactly what you see. You see this kind of dipole-like strip, which corresponds to the stray field of this 19th layer. Okay, fair enough. So it behaves as you expect. So then what happens when you start applying an in-plane field? So here what we do is we apply a field along this direction, in the x direction on this slide, and we increase the field more and more and try to polarize the system slowly. And what you can see is that for quite a bit of field, up to 200 millitesla, not much happens. It stays more or less the same. And then suddenly at right around 203 millitesla, the equivalent of one layer flips. Right? You see one layer's worth of signal flipping, and it completely flips all the way at 250 millitesla. And then after that, what you start seeing is more layers flipping, and they all start flipping from the region, let's say, of highest tensile strain, which of course makes sense because this is the region that has the weakest interlayer antiferromagnetic coupling. Okay, and then here more and more of this flipping is born from this region, and then eventually the entire system has flipped. To understand this, let's say at least from a cartoon point of view, you can see here what's going on. What we know in this part here is that the bottom layer flips first, because from our measurements of the stray field of this 19th layer, we know the orientation of the top layer, and we know that either the top layer or the bottom layer should flip first, because those are the ones that where it's more energetically favorable. And then after that, we have no idea which internal layers are flipping, because they all look the same to us from the outside. Okay, you can also do this experiment on what I would call a pristine flake, so a flake that has not been bent, that has no intentional strain, and what you will find is quite a different polarization image, where instead of having the polarization start from the middle of the sample, it seems to start from the edges, but the reversal or the polarization of the sample happens all in a much more restricted field range. You can also look at this in a different way, so you can essentially do like local hysteresis loops, so you can park your tip in this region and plot as a function of the in-plane applied field how the stray field looks, and you can see here the flipping of one layer, two layers, and then multiple layers, and then if you go to a region of less tensile strain, you can see that this flipping happens later and later, and you can see here that there's a gradient essentially from the back to the front of the sample. If you look at the pristine sample, actually everything is bunched up closer together because the strain and homogeneity is much less, and you can see that if there is a gradient at all, it's happening from the inside of the sample to the outside. So it appears that there's some unintentional strain applied to the ends of the sample, perhaps from the exfoliation. Actually, all of this is relatively simple, so you can model all of this using quite a simple micromagnetic model. So you can give the micromagnetic model this calculated pattern of strain, this inhomogeneous map of strain on the sample, and you can say that the interlayer exchange coupling is proportional to that strain, and if you just tune that parameter, you can match almost everything that you measure experimentally. So you can both simulate the kind of images that we measure here in space, and you can also simulate the kind of polarization curves that you measure using this kind of micromagnetic model. So it seems here that the dependence on strain is really what explains essentially everything that we measure. Even things that look like they might be due to defects or so, they actually have to do with the specific distribution of the strain in the sample. Okay, so let me now discuss the last system that I wanted to discuss, and this is one that you can also talk to Paritosh about because he was involved in this, and it's the subject of his poster outside. This is microscopy on a monolayer chromium phosphor sulfide. So this is a very interesting magnet because it's, again, A-type. In this case, it has a slight out-of-plane anisotropy. These are antiferromagnetically coupled layers that have a ferromagnetic intra-layer coupling with a slight out-of-plane anisotropy. The out-of-plane anisotropy is extremely weak, so that brings it, let's say, close to this idealized 2D system with almost no anisotropy. It has a kind of low Curie temperature, but not so low that we can't measure it in our 4 Kelvin system. So we got some very nice samples from our collaborators in the POGGIO group at the University of Geneva. This is, unlike the chromium sulfur bromide, a very difficult sample to deal with because it's extremely air sensitive. So you have to encapsulate it in hexagonal boron nitride before it can see ambient conditions. Otherwise, it will essentially dissolve. And it's also rather difficult to exfoliate, and so it was quite a challenge for them to get samples like this where there are regions of 1 layer, 2 layer, 4 layer, 5 layer, so that we could measure what happens as a function of the layer thickness. Okay, so the study here was really to see what happens here in the monolayer. How is it different from the other regions of the sample, in particular the 5-layer region, where you would expect to have 4 layers underneath compensating and then 1 layer on the top. So you might expect naively that it should behave just the same as the monolayer. So first we try to image the monolayer, make sure that we can image its magnetism. So this is just an optical image of the monolayer. And here you have the map of the out-of-plane stray field made with the scanning squid on cantilever. And what you can see here is basically a polarized flake with a rather large out-of-plane applied field of 800 millitesla. Okay, and you can see it's relatively uniform, but if you then go into detail and, let's say, convert this, so this is, of course, in this case we're quite lucky. We have a single layer, which is magnetized out of plane, so the spins are in 2D and out of plane. This is a case where we can invert the Biot-Savart law, and we can basically reconstruct what is the magnetization underneath, and that's what this map is here. And if you do this actually carefully and numerically, you can come up with a number for how big a magnetization this is. So what is the size of the magnetic moment per nanometer in that region? And you can essentially plot that, and you can see actually that. So this is essentially the size of the magnetization as a function of the applied field. So we took lots of these images at different applied fields. You can construct essentially what is a hysteresis loop for a single monolayer. And you can see here that this is normalized in terms of Bohr magnetons per nanometer squared to about something like 5 Bohr magnetons per nanometer squared. And that's quite a bit lower than what you would theoretically expect as a saturation magnetization for this sample. So this is, say, initial magnetization, initial indication that perhaps this monolayer, the long-range order in this monolayer, is being suppressed by the fact that it's a 2D system. We can't be sure that it's not for other reasons, but this is a good indication. Another indication is that you see we find no magnetic resonance at 0 field. Okay, so there's essentially no measurable magnetization when we go to 0. And what's very interesting is to contrast this to the behavior of the 5-layer region of the sample. So the 5-layer region of the sample would have 4 layers on top of each other, antiferromagnetically coupled, and the last layer should be providing essentially the same kind of signal as the single layer. So what we can do is essentially study the monolayer and contrast it to what's happening in this region here of the 5-layer. And you can sort of see this already here. If you go from high field around 770 millitesla, and you reduce the field close to 0 and then go into reverse field, you can, if you look carefully at the contrast, the monolayer has flipped, so it seems like it flips across 0, and the 5-layer region has not flipped at all. So it demonstrates some coercivity. And you can look at this, of course, more carefully. You can make essentially plots of this. something like magnetic hysteresis plots. And this is the red stuff. This is, again, the monolayer, and the blue thing here is what you observe in let's say, one side of the hysteresis loop of the 5-layer, and you see that there's a coercive field on the order of 25 to 50 millitesla. So quite a different behavior. Now, this is just one sample that we've measured. We're in the process of measuring more. We need to put this on firmer footing, but it seems to be an indication that there is really something happening here as a function of atomic layer thickness. Yes, so we could, that's another indication, so we could not saturate it. So it keeps going, and we would like to go higher and higher. We reached the limit of our magnet. At some point, above 1.5 Tesla, we reached the limit of the squid. And maybe that's the time to use the nanowire technique, because the nanowire we could go even higher fields. So in the monolayer, it's not clear why it's not saturating. This is one of the things that at least our collaborators in the POGGIO lab, they did transport measurements on the monolayer, and their suspicion that there's something going on with the suppression of the order has also to do with this. Okay, so actually with that, I'd like to just throw up some references. If you're curious about the things that I've talked about, please have a look at these things, and I'm happy to